Hi, everyone. Welcome here. As Junichi said, this program started in 2006. And in 2006, I taught a class at cSplash. I was actually not a mathematician then. I'm not sure I am still now, but a bit better mathematician than I was then. And so hopefully you guys will get to see a better class than I gave then. Then I talked about the good old incompleteness theorem, and I'm still not sure I understand it now, so I'm not sure what I was talking about. But I think the students had fun, and the idea is to really just get what you can from the classes and mostly interact with the other students and realize that it could be fun to do math. And I'm still here 10 years after at the Cerfon Institute, and hopefully we'll see you in a few years here. OK, so today I prepared a little presentation around the general topic of my research, although I won't talk about my research, but things that are for the general public. But the idea is that I don't have to finish the presentation. If you want to interrupt me every single second, that makes me even happier. That's the whole point. So just raise your hand whenever you have a question. If it's confusing, just tell me right away. We have no idea what you're talking about, OK? That's much more fun than finishing the presentation, getting to the end, yeah, we did it. What did we get out of it? Nothing. No, that's not the point, OK? So I don't have a goal. OK, so let's get started. So you see, my affiliation is the Cerfon Institute. That's this building, the Cerfon Institute. Who knows what Cerfon is, or who Cerfon is, or is it a what? Is it a person? Does anyone know? There's no shame here. When I was a PhD student at MIT, I first visited Cerfon. I had no idea what Cerfon was. It sounded French, which was good for me because I'm French. But in French, courant can mean the stream in the water. So I thought, oh, they do fluid dynamics. So I see it's like a metaphor. And actually, that's not the case. So even though courant does mean stream in French, and it is a French word, actually courant is named after this person, Richard Courant. And despite what his name suggests, he's actually was a German mathematician, then became American. And he founded this place. So what happened is, it's a bit a sad story that happened to many German mathematicians at the time. If you look at the dates, they overlap World War II and the Third Reich, the Hitler time in Germany. And so Richard Courant was a Jewish person. And even though he was very smart, Hitler was very stupid. He said, get out, OK? And so he started to be scared about his life and moved to the US. And many of his colleagues said in the US knew how smart he was. He was a very smart mathematician. I'll tell you more about him in a second. They knew how smart he was, so his colleagues said, why don't I arrange that you find a position at NYU to be a professor? And so he started like that, and he was so good at it, they said, why don't you start a math program at NYU? At the time at NYU, when he arrived, there was one full-time math professor, OK? And so he was so good when he arrived, they said, why don't you start a math program? He started it. He was so good at it that now we have 60 professors of mathematics here. And I hate to say because I'm part of it, but I think we're ranked among the top 3 or sometimes number 1 program in applied mathematics in the world. So I think he did a pretty good job, OK? And so he did such a good job that after he started the math program, in 46, they asked him, why don't you even build an institute with research money and people coming from all over the place? And that's what he did. So a little nugget of information is Richard Courant did his PhD under the guidance of a god of mathematics. His name is David Hilbert. Who's ever heard about David Hilbert? David Hilbert, well, good. A few of you. I didn't at your age, so don't worry. David Hilbert was like a super brain, you know, the kind of people you encounter and you get intimidated. He was just so smart. He was so influential in mathematics, so influential that I think at the beginning of the 20th century, around 1900, he came to a big convention of mathematicians and said, here are a list of 23 problems I think we should all work on because I think they're interesting for the next 150 years. So he laid out the problems, 23 problems. You can look them up. And a few of them have been solved, but a few of them are still open. So there you go, a task for today. Just finish that. Don't tell anyone, just me. We'll be very happy together. OK? And so he laid out 23 open problems, and some are still like very important problems in mathematics that everyone wants to attack. No one is perfect, though. Some problems he stated so vaguely, so sloppily, that we'll never be able to decide if we solved it or not, because he was a bit too general. So it's a word of respite that at least we have a chance to sometimes be as good as him, because he was sometimes sloppy. OK, so back to Courant, because that's going to be the gist of all of my talk. So what were Courant's contribution to mathematics? So with his advisor, David Hilbert, he wrote a textbook, Methods of Mathematical Physics, which is basically a summary all a physicist like me has to know about mathematics to solve a problem. He wrote that in 1920, and I still wish I could understand all that's in that book, because they make me a very good scientist. So one day, if you want to keep pushing in mathematics, I recommend that book, and especially applied mathematics, I recommend that book. But it might be a bit intimidating for the moment. So in the meantime, he also wrote another book, much lower level, called What is Mathematics? And here, what's great is no piece of cake. Don't get me wrong, okay? It's not like reading a novel. It's not reading Harry Potter. But still, even though it's hard, he doesn't assume any prior math knowledge. So if you're patient and learn, follow each of his reasoning, in principle, you can follow the whole textbook without having gone to university, taking advanced math classes. So it's really great. And he's able to cover the whole range of topics we still work on research-wise in mathematics. So it's a great book. And so I was reading about the famous mathematician who had found this book in his high school library, opened it, and had the revelation of his life. And because the point is, Courant makes you feel what doing math at the university is, both in undergraduate, but also doing research in math, what that means, what type of questions we try to answer. And so it's a good read if you want to sort of feel what mathematics is. More linked with our presentation today, Richard Courant is also the inventor, although it was sort of not taken on immediately, it took 30 years to be taken on, the inventor of a technique for solving equations, for solving hard problems, called the finite element method. What is this method? Let's say I have a jet engine and blades, and I want to know what happens if a goose hits the blade and breaks the blade, and then the engine possibly goes down. That's what happened with the flight that landed on the Hudson River. They ran into a flock of geese, I guess we say in English, and they lost both engines, and so they had to land on the Hudson River. And what happens when you hit geese, it's a bit sad, but it's sad for the geese, sad for the people also, it's sad for everyone, it's a very sad story, is you lose blades and you might lose the engine. And so you want to make sure that that thing doesn't burn or doesn't explode if you lose blades, because those blades rotate so fast. So the equations are so complicated, you have to run intensive computer simulations, right? You take a big computer and you run the problem. But how do you solve the problem in the computer? And that's what Richard Courant invented. He said, if I have to solve the solution everywhere, it's incredibly complicated. You see how the color changes. Here it's red, very high stress. Stress is the force on the reactor. Here it's blue, low stress. Seems like the solution is complicated. There's no way I'm going to come with a nicely behaved solution everywhere. What I'm going to do instead, and that's the finite element method, is I'm going to cut the whole shape into little squares, and on little squares I'm going to consider very simple solutions. Let's say linear, just a straight slope. But if the square is small enough, you can make very complicated functions by patching linear functions together, right? By patching simple solution on each square, if you patch them together, you can make a whole complicated shape. And so that's the finite element method. And so what I want to tell you about that is this is still very much in the spirit of what we do here. I'd say 99.9% of the faculty here and the students here, they do math inspired by physics, inspired by engineering, inspired by Google, Facebook, questions that are given to us from industry, from science, and we want to come up with a math that they need to move forward. And Richard Courant was fully in that spirit, doing that. And you see what's cool about math? He came up with his method. He didn't even have a computer, just came up with it in his mind. And 30 years later, in the 1960s, we started to have the first decent computers They're not nearly as good as your cell phones right now, but at the time that was very impressive. And so 30 years later, they could take on his idea. So in math, what's cool is you could be ahead of the curve by 30, 50, 100 years and solve cool problems that people are going to use later on. OK, so now I'm going to show you, again in the spirit of applied mathematics, how mathematics comes in for my topic. What I work on is nuclear fusion. OK, so what is nuclear fusion? Nuclear fusion is based on the following fact of physics that people have measured and observed. If you take a proton and a neutron together, that's called deuterium, it's D. Proton and neutron together, deuterium, and you make it collide very closely with one proton and two neutrons, which is called tritium, T. Out of this reaction will come helium, a neutron, but 17.6 MeV. What is the thing MeV? Never heard of that. Well, it's a weird units that physicists like you use, but the bottom line is what you want to care about is each reaction is 1,000,000 times more powerful than the reaction of burning coal or burning gas or burning gasoline. So, and this is one of the reactions similar to reactions that are happening in the sun. So what we're thinking, what we're hoping to do is make those reactions happen in a power plant. We're going to make way more energy than if we burn coal. And plus, it's going to be fairly clean energy because helium is a nice gas. OK, and the neutron you have to be a bit careful about. But it's not like you make plutonium or horrible stuff, right? So that's what we want to try. And what's good with that is because it's 1,000,000 times more energy per reaction, if I want to power Manhattan for 1 year, all your cell phones, chargers, all our computers, all our microwave ovens, all our fridges, I need to fill Yankee Stadium with coal all the way to the top. How much deuterium and tritium do I need to power Manhattan? The back of a pickup truck, because I divide by 1,000,000. OK, so that's why we want to do that. What is the difficulty? The difficulty is you all know that proton is plus charged. This is also plus charged. Those guys don't want to get close to one another. The metaphor I like is they're so busy, both of them, they never want to go on a date. Once they finally find a spot in the schedule to go on a date, then they really hit it off, and they're so happy they give us energy that it's a free-for-all. OK? So how to make them go on a date? To make them go on a date, you have to force them. And to force them, that means that you have to give them so much energy, so much velocity, that even though they don't like each other, you have your friend, come on, talk to her. Come on, talk to him. So that's what we're going to do. We're going to give them so much velocity that they won't have any choice. They'll go to that movie. OK? So what does it mean to give velocity in a fuel is you heat it up very high, to a very high temperature, right? High temperature means everything zooms by very fast. OK, so what's the bad news for us? Why am I still in this job? Why am I still doing research? And why don't we have free energy for everyone? Well, they really hate dating, and they don't know that they should date, because the velocity you need to give them corresponds to a temperature of 100 million degrees. For comparison, the core of the sun is 5 million degrees. OK, so that's insanely hot. So what do? Well, if you go to Kmart and you say, excuse me, sir, would you have a box where I could put stuff that resists 100 million degrees? The guy's going to think you're a lunatic. Because you cannot find that, right? So for 100 million degrees and you have this fuel and you try to contain it, the containment device is going to melt. The good news is because it's so hot, in fact, the plus and the minus charges are flowing freely. So the idea is you can use magnetic fields to confine the particles, to keep them from hitting the box. What do I mean by that? Don't panic. I'm going to explain every detail. It turns out it's a fact of physics that if you have a particle that's charged with charge q and has a velocity v, and you impose the thing called a magnetic field, then the particle feels a force on it. There's a force on it, which is q times v cross b. Who has already seen that thing called the cross product? Just a few people? Okay, that's okay because I prepared a whole slide to explain. So what is a cross product? Who knows what a vector is, first of all? Okay, so a vector is just an arrow. It's just a direction and a magnitude. So we're saying that if the velocity has a certain, how to calculate this cross product? If the velocity has a certain direction and magnitude, and the magnetic field, which I'm going to tell you about more in a second, has a certain direction and magnitude, to get the direction of f, you have to take the direction that's both perpendicular to both v and b. That's what taking this cross product is. So I'm going to show you in a second, and then we'll go back to that slide. So see, if I have two vectors, v and w, I take my right hand. So let's say the particle goes with velocity v, the magnetic field is w, then the cross product tells me that the result is a vector that's perpendicular to both the thumb and the index finger. So if I apply that to my situation, let's say the magnetic field is going into your board, into your face. Let's say the velocity is this way, so let's do it. So let's say the electron, this particle goes up, the magnetic field is towards you, so the force, let's see, why is it not working suddenly? Oh yeah, no, because I have to be, okay. Okay, so, wait, okay. I just didn't plot the thing, say, okay. What's going on? Oh yeah, because there's a Q multiplying it, okay? So let's go back. It's here. What's the charge of the electron? Is negative, okay? So negative V is down. Magnetic field towards you, what's this guy pointing towards? Towards the inside, okay? Let's go to the ions. The ion, let's say, goes up. Magnetic field towards you, force also to the inside, okay? So if I'm able to apply a magnetic field, if at first the particles do whatever they want, now they feel a force always towards the magnetic field, always towards the green, right? And so here they're free to move any direction, and they hit the walls, and it's bad and melts the wall. Here I apply the magnetic field, they're forced to be stuck on the field line, and they never touch the wall. Okay, so that's the first thing is calculus and vector algebra. You'll learn, if you ever take mathematics and take calculus and vector algebra, you'll learn about this cross product, and that's the first part where mathematics comes in for fusion. Okay, there's a problem, is it turns out that the cross product always also says that if the velocity is the same direction as the b, the result is a zero vector. So that means that along the direction of b, there's no force. The particle can go as far as it wants along b. It's forced to be close to stay close to the green line, but it can go left and right as far as it wants. So people forgot about that and first said, okay, we're going to get fusion with a cylinder. But in the cylinder, the magnetic field goes like that. And so at some point, your machine stops, but the particles are free to move along the magnetic field as fast as they want. They all leak out. Do you see how they all leak out? The magnetic field is horizontal. The cylinder is stopping at some point, so they all leak out. So that didn't work. So if you have a cylinder, it doesn't work. Particles are going to leak out. So you're going to need a shape that closes on itself. And so people asked what shape closes on itself that has the magnetic field never going into the wall. We never want the magnetic field to go into the wall because we never want the particles to follow the magnetic field and hit the wall, melt the wall. So that turns out also a question of mathematics. Mathematics comes in everywhere. It has a pretty nice name. So it's a question of algebraic topology. Sorry for the swear word. It's a field of mathematics. And it's called the hairy ball theorem. Okay? So it's a nice word. Mathematicians are funny people. And what it says that if you want to calm a sphere, you always guaranteed to have, if you want to calm a sphere and never have a zero vector, never have no hair somewhere, you're forced to have a cowlick. However, if you calm the hair of a donut, it's sort of disgusting to think about, but if you imagine hair on a donut, there you can calm it perfectly with never having hair sticking out. So if our heads were donuts, we'd never have cowlicks. Okay? We could comb it perfectly, and it would never stick out. So you can be mad at Darwin or God, depending on what you think, for not having heads like a donut. But what's good is we're going to use that for fusion. Because we're going to say a sphere is bad, because at some point I'm going to have a magnetic field that takes my particle out to the walls, that's going to melt it. However, why don't we have a torus? You see if a particle follows the hair, it just follows nicely, it never hits the wall, always stays on the torus. Do you all see that? Is that clear? Is that clear? Okay, so that's the hairy ball theorem for you, applied to fusion. Okay, and so in real life, that's what we have. This is the device we do for fusion, is we use a torus, and let's do it once more. So we've decided now, we've showed, thanks to that cross product, that particles follow a white line, and you see if I follow a white line, I'm sometimes on the inside, then I'll come up back on the outside, and I'm always on the surface. So now I can imagine putting a wall around here, and the things are never going to touch the wall, ever. I'm never going to melt my device. So I don't have to go to Kmart and ask for a magic box. Okay? So we think Homer Simpson knew about that. See? That before donut, fusion sucks. Donut, let's try. Oh, now fusion has a promise. Okay? Now we're happy. So it turns out mathematically that a donut doesn't have to be a nice donut like you buy in a shop. This is also mathematically a donut. It's a donut if you imagine the baker, having a fancy machine that rotates, that torsades, that rotates the donut. It's also mathematically a donut. And maybe fusion people are masochistic. No, in fact, there are reasons. This is a device we also consider. And I'm going to show you this is much more complicated to achieve, but mathematically, it's also a donut, even though it turns on itself. And who knows what a donut is called in English, by the way? I just said. In math. Yeah, you want to say? Torus. Yeah, a torus. Okay, so the mathematical word of a donut is called a torus. And so this, topologically, is that dirty word. This is equivalent to a torus mathematically. So what does it look like in real life? In real life, that's how we do it. We have those coils that are responsible for making the magnetic field. And so once the magnetic field is made, the fuel stays in that pink region. Okay, the fuel stays in that pink region. But you see, from the point of view of an engineer, it's much more complicated than from the point of view of a theorist. Oops. That's for me, for the theorist. Much cleaner. But in real life, just like that. And so I want to show you when I'm going to go inside the device of like that at MIT to see it, so you get an idea what it looks like. Okay, so there we are. We're inside the device. Okay, and so you see the empty space is where the red of my figure was. That's where the fuel sits. And this is the wall to protect, because every so often particles knock each other to the wall, so you still need a wall. And so we can walk around. Let's see if it works. Yeah, I'm walking around, and I'm going to show you something. So let me go. How do I go back? Like that. It's Google Maps in the tokamak. Okay, look. Okay, so I'm going to explain to you, if we get there, this is like a massive microwave oven to heat up the fuel, okay? Because we need to get it to 100 million degrees. And so basically, we shoot massive waves into the fuel. But I'll go back to that. The one thing I want to show you is you see, well, it's a bit hard with this contrast. But initially, everything is polished perfectly. It's a fancy material called molybdenum. It's polished perfectly. It's basically a mirror. And so every so often, particles get knocked out, and they hit the wall, and they're so hot that I don't know if you can tell. It's a bit hard to tell with the contrast of the device, but you see it starts to be dirty. Do you see marks here of different colors, gray and so on? That's the particles hitting the wall. That's what you want to avoid because you're destroying the machine. Unfortunately, thanks to magnetic field, we avoid that as much as possible. And let's see if we can zoom. You can't quite see, but here you can even see a tile that melted. There's a part that melted here because it was just too hot at some point. And so, by the way, I'm being lost. Okay, well, okay. By the way, if you want to clean up the device, you have to enter through that port, and you can imagine the environment of the experimentalists and the engineers who are here. And that's why maybe you're happy to be a mathematician. Okay. Okay, so that's it for this looking how it looks like. Now I have to find out how to close that. Do you see where I close it? Yeah. OK, and so that's how it looks in real life. You see now to scale with a person inside, cleaning up those tiles that I was talking about. And now that's this other torus, and you see it's way more complicated. You have coils in every direction to make this bending stuff happening. And so that's complex. I'll go back to that in a second. OK, so back to mathematics. So if we want to understand what really happens, what can go bad and what can go right, well, one technique that was invented by this French mathematician and scientist, very famous, Henri Poincaré, is he invented this technique. He said, look, at every angle the long way, it's the same, right? This thing is periodic. So particles always come back through a plane here, through some plane at this constant angle. So a good idea for me is to cut here and follow a guy, and whenever it hits that plane, I want to see where it lands. So that's what I did for you here. So let's say the yellow surface is the red surface. Okay, the yellow surface is the red surface, and you can imagine that the green surface is inside the red surface, but let's focus on just one surface. So the yellow surface is the red surface, and I follow a field line. That's what I did. I solved it in my computer, and whenever it came back, so I followed it. Whenever it came back, I recorded the point. And whenever it came back, I recorded the point again. And whenever it came back, I recorded the point again. And here I'm, yeah? Yeah, so what I'm saying is, imagine I have a flat plate, a flat board, and I cut the torus here. I cut it here with a flat board. I just want to see what comes into that board. You see, I have my donut like this, and I cut it like this. And I want to see where the field lines, the gray lines, come back every time. Another question? Yeah? Yeah, very good point. So all those points on the yellow curve, that's exactly what that's the perfect question. That's exactly what I wanted to check with that calculation. All the points on the yellow curve come from one particle, just sampling the whole thing. And that's great news, right? That's exactly what we wanted. We checked that the particle never wanders off, in or out. It's stuck to that red surface, which is yellow here. Now I followed another particle, which was more on the inside. And this guy also follows a surface. Great news. So it's like an onion. I have shell of shell of shell of shell, and they all stuck on their shells, and none go to the walls. Okay, and so people did that. Actually, let me skip that one. People can do that, can experimentally verify that. I'm not going to explain to you why, and you see they get the same thing as my figure. So indeed, in experiment, you can have those nice shells where the particle never leaves off. What can go wrong, however, is first let me again, that's mathematics. Now it's the mathematics of dynamical systems. So again, another field that you might be interested in at some point. And let me say that the short angle around the donut I call theta. Theta is a Greek letter. We use Greek letters just to impress people. That's mathematics, right? If we use only A, B, and C, people would think that we're doing easy stuff, which is true. But we use Greek letters to make it look hard. So theta is the angle the short way, and phi is the angle the long way. Okay? And now I'm going to measure, if I follow the magnetic field line, for an amount delta phi, for a small amount in phi, how much do I go around in theta? If I follow a small amount in phi, how much do I go around in theta? Well, it turns out if that number is a rational number, then I'm going to come back to my position. Why? Because if I go, so that says that delta theta is p over q delta phi. So if delta phi is 2 pi, if I go an amount 2 pi around, my delta theta goes only p over q times 2 pi, so it goes some amount. Then I go another 2 pi, it goes 2p over q. Then I go another 2 pi, it goes 3p over q. And when I go q times around, it's qp over q, which is p 2 pi, which is a full time around. Okay, so I've come back to my position. And so this is exactly, you see how this surface here is different? This here, I picked a rational number. The slope of the magnetic field is a rational number. And so because a rational number, I only go a fixed amount every time. and I don't cover the whole surface. And only whenever I come back, I always only ever cover those points. Here I picked a irrational number. So irrational number, I cannot fully come back. I never come back exactly to the same point, so I cover the whole surface. So the difference, see, number theory comes in also in this topic. Rational number, I come back to the same position every time. Irrational, I cover the whole surface. Yeah, another question?
The experimental section that you showed was not perfectly circular.
That's right. So actually, I'm doing circular for simplicity. It turns out that for reasons way beyond what we want to talk about today, it's better to not have circular.
Is the angular velocity of theta constant?
No, it's not. Very good.
Okay.
Yeah. Okay, so now what happens? So this is the situation if I'm perfectly symmetric around the phi angle. But in real life, I have a fixed amount of coils. In real life, I can never make a fully perfect symmetric, a thing that doesn't depend on phi. There's always some variation, some imperfections, and so on. And look at what happened when I added some imperfection mathematically. Now I created what's called islands. You see those islands sitting here? Now, particles that are here, they never sample the whole region. They sample only this island. When I follow the field line, they actually come back here. And when they follow, they come back here. And you see now I make the imperfection of the magnetic field even worse. Now you start to have some fuzziness here. And that's called chaos mathematically. That's chaos. And so I added the imperfection a lot, and I got full-on chaos. And that's really bad. That's what you want to avoid in a machine. Why is it really bad? Because now, remember that our whole point is we want the particles to always follow the same surface, to not have massive radial excursions. But here, if I follow a field line in chaos, it's a fact of mathematics that a field line can go arbitrarily far from its original point. So let's say I start here. Maybe the particle comes here, here, here. And you see the excursions are massive. And so that's terrible. And then it can hit the wall. OK? So you see the ideas of dynamical systems and chaos, which I talked about today, also come in fusion. And it turns out that KAM, which is Kolmogorov, Arnold, and Moser, I mentioned that because Moser was a professor here, they came up with a theory that if the number corresponding to the slope of the magnetic field is irrational, so again, number theory comes in, then I'm going to have some surfaces resisting. See, you still have some nice surfaces that survive. And that's because the number was irrational. If I'm a very low rational number, like 1/2, I'm going to be fully chaotic. So mathematics comes in here. Okay, maybe the last thing I'm going to talk about, because we're maybe getting tired and we want to save time for questions, is I promised this is how we heat up the plasma, the fuel. Let's say we never talked about plasma. How we heat up the fuel is we use massive microwave ovens. Does anyone know how your microwave oven works? Let's see someone. Do you want to raise your hand? No? OK. OK, so then same person.
The water in the food gets heated up by the microwaves because they make it vibrate.
That's right. So microwaves, what are microwaves? They're basically electric fields, magnetic fields, just like you use for your radio station or for your cell phone, that are sent inside the chamber of the microwave oven. They bounce on the walls, and they're chosen to have exactly the right period, the right frequency to excite the water molecules inside your pizza. And so the water molecules inside your pizza move, and they heat up everything in your pizza, and that's why your pizza is warm. And that's why you don't want to stand next to your microwave oven, because so if you look at your microwave oven, there's always a grid, right? Either like a stripes or even dots. And that's to protect the wave from going outside. They block the wave. But there's still some leaking out, so you don't want to put your head right next to the microwave oven when something is heated, because you don't want the water molecules in your brain to be excited, because otherwise it heats up there, and that's not good, I promise, okay? You don't want to heat this up, okay? Well, we do exactly the same thing. We choose the wave that likes to excite those fuels, the particles in the fuel, except for us to reach 100 million degrees, we just have it 1,000 times more powerful than your microwave oven. So there, not only do you not want to put your head, but you don't want to put your body, okay? So nothing, okay? So what is it physically? Well, physically, it's the same phenomenon. I don't know if you've ever seen that. People on a wakeboard, if you do wakeboarding on a wave, and you choose to always be in the right part of the wave, right behind the boat. You see the part of the wave that goes down towards the boat? You don't even have to hold the rope. The wave's going to keep pushing you, right? It's like you're going down on the slope, but the slope keeps moving, so you follow the boat. So you can look, I recommend, I spend too much time doing that, look up videos of people wakeboarding without the rope, is because they are exactly at the position and in phase with the wave of the water. Yeah? That's right. I'm going to talk to you about that. I'm not there yet. But yeah, lambda is the wavelength. Very good. Okay, do you understand this physical picture? Yes? Oh yeah, 5 minutes. Yeah. So if I'm on the slope here, I can follow the boat and can use the energy of the boat essentially to move forward. Well, this is exactly what our fuel particles do. We send them a wave, which looks like that. It's wiggly, except it's electric field. And it's charged, so it feels an electric field acts on the charge. And if you make sure that the velocity of the particle, so v is distance over time, right? So the distance that matters here is the wavelength. The wavelength is the distance between two crests. And the time that matters is the period. T is the time between two crests. So if you choose your velocity, if you have your velocity of the particle to agree with this condition, your particle is going to be carried along by the wave. It's going to gain energy. Okay, so what we do is we choose our microwave oven. We know the velocity we want to have. We know the temperature we want to have in the device. So we choose lambda. We choose the microwave oven that we need to satisfy this condition. Why do I mention that mathematically? It's because when that happens and you want to calculate physical quantities, it turns out the object that comes up is this object called an integral of lambda divided by lambda minus tv. Who's seen what an integral is already? Okay, a few people. That doesn't matter if you've never seen it. What integral is, see, it looks like a weird S. It's a weird S like the Frenchmen would write in the 18th century. Because an integral means a sum. It's a sum for all values of v. All single values of v, I sum this quantity lambda over lambda minus tv. This is what the integral dv means. For all value of v, I sum this quantity. So now what happens? And we'll finish on that. What happens is that we said for resonance, I need v equals lambda over t. Let's plug this in. V equals lambda over t. The t over t cancel. So I get lambda minus lambda. I get 0. A 0 in the denominator? That's bad. I never want to see that in mathematics. Unfortunately, that's what the physics wants. So what do? Well, mathematicians realized that the way out is to view actually this quantity t, the period, as not a real number, but this thing called a complex number. The complex number is a real number plus I times another real number. And what is this weird number I? It's a number such that the square is negative. I squared equals minus 1. I is a purely imaginary number. And so what mathematicians found out, and I just want to tell you the main message, it's okay if you cannot follow that, that's the new thing, is that complex analysis, which is a whole beautiful field of mathematics, also come in for applied math. And what you find out is to calculate this integral, you should not sum all the values of v which are real, you should actually consider a so-called complex plane where quantities have an imaginary part and a real part. And so you should follow a weird path in the complex plane, and then you can calculate this integral. So the last thing I'll mention is all these topics of wave-particle resonance is very hot in mathematics right now. There's a lot of rigorous math. We, the physicists, we sort of know what we need to know. But there's a lot of rigorous math that needs to be done. And one of the first people to do it very rigorously and very carefully and beautifully is this French mathematician, Cédric Villani, here. And he was awarded the Fields Medal for that work. Do you know what the Fields Medal is? The Fields Medal is the most prestigious prize in mathematics. It's sort of like the Nobel Prize of mathematics, except it's reserved for people under 40 years old. So I'll soon not qualify anymore. You still qualify for a while. And so the Fields Medal, if it's your goal, that's a nice goal because it's a great prize to have. It's a huge recognition in mathematics. Okay, so let me jump to the conclusion. I won't cover that. So what have we seen? is that we've seen many fields of mathematics, algebraic topology, complex analysis, number theory, dynamical systems, chaos, all come into play to help push fusion forward and get to fusion. But there remains lots of unresolved questions, even questions that fusion people don't care about, but that rigorous math needs to be done on. And so in all those topics, dynamical system, like I said, analysis, partial differential equations, we haven't covered that. Numerical computation, we haven't covered that. And like I said, among these questions, if you like pure math, there's a lot of pure math you can do. If you like applied math, there's a lot of applied math you can do. So you should join the boat at some point. It's a lot of fun, really, I promise. And so I know this went fast. This will be available online. But if you have any questions or want to contact me for any reason, this is my email address. And it's been a pleasure. And let me know if you have any questions. OK? Thank you.